Hello everybody! Thank you for attending my presentation with the title Analysis and Experimental Verification of the High Voltage DC Bus Current and Voltage Ripple in Electric Vehicles. My name is Marius Gentjon and I work as a Research Associate for the Power Electronics Department of the Technische Universität Berlin. I'm currently dedicated to the SIGWELL project, which investigate the impact of power electronics on the battery aging in electric vehicles. Let me give you a short overview. First, I want to introduce you to the current ripple in the DC bus of electric vehicles and its impact on the battery aging. After that, I show you a simulation model. With the simulation model, the current and voltage ripple can be estimated taking into account the full drivetrain of the vehicle. In order to validate the simulation model, I measured the real current and voltage ripple in an experimental setup. Then, the validated model is used to go into a parameter study and to understand the main effects of speed and torque on the current and voltage ripple. Finally, I will sum up the results and give a short outlook. So, what is the current ripple? The current ripple is an AC current which is overlaid on the DC current. To understand how it occurs, let us have a look at a simple representation of the DC bus. The battery supplies a DC current to the DC bus. By switching its semiconductors, the inverter converts the DC current of the battery to an AC current suitable for the motor. The switching produces an AC current overlaid on the DC current of the DC bus. In electric vehicles, the battery is the most expensive single component, and its aging is of great concern. Among other effects, the current ripple on the DC bus can increase the capacity loss of the battery, as two studies show. The capacity loss depends on the frequency of the overlaid AC current. However, both studies detect different frequencies as critical. For example, 1 Hz on the left and 15 kHz on the right. So it is not clear if the switching frequency of the inverter is that critical for the battery aging. The SIGWELL project is currently investigating the battery aging due to the current ripple, so hopefully there will be more information on this soon. Let us come to the model description. I include the full drivetrain in the simulation of the DC bus current and voltage ripple. In doing so, it is possible to see the impact of torque, speed, and battery voltage. This works in the following order. For a given test scenario, the operation point is derived analytically and the set point for motor and inverter control is taken from lookup tables. Then, the DC bus current and voltage ripple are simulated with the software Plex. Finally, the ripple is analyzed in time and frequency domain. To derive the motor set point, the DC link voltage is calculated. Due to the voltage drop over the DC bus, the DC link voltage is lower than the battery voltage for motoric operation points. The motor set points require the AC RMS current, seen in the top plot, the modulation index of the inverter given in the middle, and the phase shift between AC current and voltage shown in the bottom plot. The set points follow the maximum torque per ampere control scheme in the fundamental and the field weakening speed range and are stored in the three-dimensional lookup table. For the accurate estimation of the current and voltage ripple, it is necessary to model the DC bus impedance. Therefore, I referred to the artificial network from a new international standard. The standard defines how to measure the current and voltage ripple of component in the high voltage DC bus. The standard is defined for frequencies up to 150 kHz, and so is the simulation model. In consequence, the shielded cables between DC bus and inverter are represented as inductances, while for the DC link its equivalent series inductance and resistance are considered. The inverter is switched with a space vector pulse-width modulation scheme. To verify the results obtained by the model, I measured the current and voltage ripple in an experimental setup. The DC bus impedance was built as defined in the standard. Moreover, a silicon carbide MOSFET inverter and an ohmic inductive load was used. This observed operation point is given in the table. Here, the measured current and voltage ripple is shown. If you look at the voltage on the right, you see high spikes due to the switching transients. Therefore, the current and voltage are low-pass filtered with the 150 kHz second-order Butterworth filter. To compare simulation and measurement, I selected two different criteria: the root mean square value of the ripple, which is important for thermal effects, and the peak-to-peak value, which stresses out nonlinear effects such as an overcurrent. Model and simulation correspond very well, as the simulated RMS current ripple deviates only 1% from the measured ripple. As we saw in the battery aging studies, the frequency involved is very important. So let's compare the spectra of the measured and simulated current and voltage ripple. Looking at the distinct peaks around 10 kHz, the switching frequency, and 20 kHz, twice the switching frequency, we see a very good correspondence between the measured and simulated ripples. The validated simulation model is used for a parameter study. More than 100 operation points in the torque speed plane are plotted in order to understand the impact of torque and speed on the RMS and peak-to-peak current and voltage ripple. Each circle represents one operation point, and its area is scaled with the amount of the ripple. The amount is also indicated by the color. Comparing the peak-to-peak value, shown in the upper plots, with the RMS value given in the bottom plots, we see a similar behavior regarding the impact of torque and speed. A similar behavior is also found comparing the current, the plots on the left, and the voltage ripple, the plots on the right. Exemplarily, the RMS value of the current ripple is analyzed in the following. Let's have a closer look to the fundamental speed range, marked in dark gray. The highest current ripple is observed in the corner point at ± 250 Nm and 3000 rounds per minute. We see the operation point of the machine has a high impact on the DC bus current ripple. For a higher torque, a higher AC current is required, which leads to a higher DC bus current ripple. At maximum torque, the current ripple rises with the speed. This can be explained with the higher modulation index involved. In the field weakening speed range, marked in light gray, the highest current ripple is found at maximum speed. Comparing it to the maximum ripple of the fundamental speed range, we see that it is even higher. In the field weakening speed range, a higher AC current enables higher speeds. This leads also to an increased DC bus current ripple. In contrast, the current ripple appears to be almost independent of the torque. The AC current and the phase angle have contrary impacts on the current ripple, which in sum cancel out each other. Let's look at the other side of the inverter, the battery. At the lower state of charge, we obtain a reduced battery voltage. For the same speed and torque, an increased DC current is required as the battery voltage is reduced. This means a reduced DC link voltage at the inverter and also a different set point for the motor. The diagram shows the DC bus current ripple for different battery voltages. Two operation points, one in the fundamental speed range and the other in the field weakening speed range, show that the current ripple rises with the reduced battery voltage. Finally, let's sum it up. Studies show that the DC bus current ripple has an impact on the battery aging. To describe and to understand the current and voltage ripple in the DC bus of electric vehicles, a simulation model was developed. A new international standard is used to model the impedance of the DC bus. In an experimental setup, the current and voltage ripple were measured. In time and frequency domain, only slight deviations are observed between measurement and simulation. A parameter study showed the impact of torque and speed on the current ripple. The highest ripples were obtained at the corner points and at maximum speed. Regarding the battery, a lower state of charge leads to an increased current ripple. The two battery studies detect different frequencies as critical for battery aging. More research on that topic might help to estimate the exact impact of the current ripple on the battery aging. The investigation shown here can also support that, because it shows the critical operation points and the current ripple in these points. Thus, battery aging can be tested with more realistic scenarios. Considering driving cycles, the simulation model can be used to estimate the system lifetime. The model includes the full drivetrain. Also, other components are affected by the DC bus current ripple, for example, the DC link capacitor. The model is also easy to adapt to new drivetrains. The motor control lookup tables can be fed with data from prototype FEM simulation or measurements. Thank you for your attention.